Hello there, dear students. This is Tamás Jávor. Welcome back to Rubber Duck Physics. Earlier you learned that forces cause objects to speed up or slow down in a straight line. But what happens when we apply a force that makes something rotate? It's time to meet the rotational equivalent of Newton's second law. Let's start with Newton's second law in its familiar form. Sum of F equals ma. This tells us that the resultant force acting on an object is equal to its mass times its acceleration. I like writing it in this form: A equals sum F divided by m. In this latter form, we see that the acceleration of an object depends on the force applied and the object's mass. It is the forces what cause acceleration, and the mass resists this change in motion. It's important to remember that Newton's second law is a vector equation. This means the direction of the resultant force determines the direction of the acceleration. Think about pushing a shopping trolley. The harder you push, the more it speeds up. But if the trolley is heavier, it takes more force to get it moving. That's Newton's second law in action. Now, in rotational motion, we have something similar. Instead of the forces acting on an object, we talk about torques. And instead of mass, we use moment of inertia, which describes how mass is distributed around the axis of rotation. The rotational version of Newton's second law looks like this. Sum tau equals I times alpha. Here tau represents torque, I is the moment of inertia, and alpha is the angular acceleration that develops. Or if, again, you want to put the causes on the right-hand side and the consequence on the left-hand side, alpha equals sum tau over I. Just like force causes linear acceleration, torque causes angular acceleration. And just as mass resists changes in linear motion, the moment of inertia resists changes in rotational motion. Also, just as linear acceleration is always in the direction of the resultant force acting on an object, the angular acceleration will be in the direction of the resultant torque acting. So, a positive counterclockwise resultant torque causes a positive angular acceleration and a counterclockwise change in angular velocity. If the sum of all torques is, however, negative clockwise, the angular acceleration and change in angular velocity will be clockwise too. It is possible to not just build the equation for angular acceleration, sum of torques, and moment of inertia as an imitation of Newton's second law for straight line motion, but to exactly prove, starting with Newton's second law and the known relations between angular and linear quantities for each point in our extended object, that the equation is true. But in this video we would like to keep it short, so we are okay with outlining this analogy only. It's also interesting that Newton himself never said this law. We just got so used to calling the relation between acceleration of an object and the factors that influence it Newton's second law, and the analogy is so tight that everyone started to call it Newton's second law for rotation. That's how your scientific success pays off in more than one way. Our honors to Mr. Newton for his work reforming mechanics. Going back to the law, once again, the meaning of it is the larger the resultant torque exerted upon an object, the greater the angular acceleration. But the moment of inertia too plays an important role in determining how much the object speeds up in rotation or slows down. The more mass is distributed far from the axis, the larger the moment of inertia, making it harder to spin up. Remember the merry-go-round. Torque, if you push it at the edge, you get more torque, making it easier to spin or to slow down than if you push or pull it close to the axis. And moment of inertia, if the merry-go-round has a lot of mass far from the center, it takes more effort to get it spinning or to stop it. Let's work through a problem. You apply a torque of negative 10 Newton meters to a wheel with a moment of inertia of 5 kilogram meters squared. What's the angular acceleration of the wheel? We start with the formula, tau equals I times alpha. Then we plug in the values, 10 equals 5 alpha. Of course, we don't have any other torques. Now we solve for alpha. Alpha equals negative 2 radians per second squared. Never forget that negative angular acceleration doesn't necessarily mean slowing down. Negative means clockwise, and if the wheel was previously at rest or it was already rotating clockwise, negative torque speeds up its rotation in the negative, clockwise direction. An important note for this question: here we have used given values for torque and moment of inertia to make things simple, so we can directly substitute into the formula we just learned. But in real-life problems, we usually get more natural inputs, like forces, lever arms, mass distributions, and shapes. From these, we could calculate the torque or moment of inertia ourselves. Don't worry though, we'll practice problems with more complex inputs in later videos. For now, this straightforward example will do. Now that we know torque causes angular acceleration, what happens if you remove the torque but the object is already spinning? Does it keep rotating or will it eventually stop? And if it does keep rotating, what energy keeps it moving? In our next video, we'll explore the concept of rotational kinetic energy, the energy that keeps objects spinning even when no torque is applied. To sum up, Newton's second law for rotation tells us that torques cause angular acceleration. And this depends on the moment of inertia. If you want a rotatable object to spin up or slow down faster, you need to apply more torque. But if the object has a lot of mass far from the axis, it's going to take more effort. Stay tuned for the next video, where we'll look at the energy behind rotational motion, rotational kinetic energy, and see how it's similar to the energy of objects moving in a straight line. If you are finding these videos helpful and want more personalized support, I offer online tutoring in IB DP Physics, as well as AP Physics, A-level Physics and Maths. You can find my email address in the channel description of Rubber Duck Physics, accessible on your web browser. Feel free to reach out if you would like to book a session. Thank you for watching the video. See you next time.